consider the synthetic applications of ethyl acetoacetate, and the first application is how to convert it to a monocarboxylic acid. Here we have considered conversion to butanoic acid. The first step is very similar to what we learned with diethyl malonate. Treat it with a base. One of the acidic hydrogens is removed to form the corresponding enolate ion. That enolate ion acts as a nucleophile, attacks the carbon of the haloalkane that we have taken. Because we want butanoic acid, we have chosen the appropriate haloalkane. Once the nucleophilic substitution is over, we subject the product to hydrolysis. This is done in two steps. The first step is to convert the ester into COOH. KOH will convert ester to COOH. In the second step, the potassium salt of the ester is converted to COOH on one hand, and this group is hydrolyzed because this is a polar group with the electrophilic end being carbon. So if you add water, oxygen will attack carbon, so you end up getting CH3COOH, which is acetic acid. C2H5O and H will become ethanol, and the rest of the molecule is nothing but CH3CH2CH2COOH, which is nothing but butanoic acid. So this is how we can convert our ethyl acetoacetate to a monocarboxylic acid like butanoic acid. We'll now consider the conversion of ethyl acetoacetate to a dicarboxylic acid, and here we are considering conversion to succinic acid. As you can see, the succinic acid molecule has two CH2 groups, and as we noticed in the previous conversion, one acetyl group will be removed. So this CH3CO will be removed, this part will be retained, which means two carbons will be contributed by ethyl acetoacetate, and therefore I must take a molecule with two carbons. So the first step is simple. Convert our ethyl acetoacetate to the corresponding sodium salt. Then the nucleophile is ready. It will attack the bromoester molecule chosen suitably. So once the attack takes place, nucleophilic substitution takes place, and then we carry out hydrolysis like in the previous step, conversion. Base catalyzed hydrolysis will convert both the ester groups to the potassium salt. Then we subject it to acid hydrolysis. Both the potassium salts, COOK, will be converted to COOH, and the acetyl group will be hydrolyzed to acetic acid, yielding what is called succinic acid. So synthetically, ethyl acetoacetate can be converted either to mono or to dicarboxylic acids or to their derivatives as we choose. Now we proceed to the third conversion, which is very similar to what we did with diethyl malonate, which is to convert an aldehyde to an alpha-beta unsaturated molecule like crotonic acid. So how is it possible to convert an aldehyde into an alpha-beta unsaturated acid? Take acetaldehyde, condense it with ethyl acetoacetate. We know very well that ethyl acetoacetate is a very strong acid, so even a mild base can remove a proton. So the first step is attack of carbon. So this becomes single bond OH. There is a new bond formed between these two. So this is similar to your aldol condensation. In the next step, what happens is that there is one more alpha hydrogen left that is also acidic, so that can also be removed as H plus, and so that OH will come out as OH minus, and along with H plus it becomes a molecule of water. So the product that is finally formed is an alpha beta unsaturated compound, which as usual is first converted sorry for the disturbance, is first converted to the corresponding ester, is converted to the corresponding carboxylic acid, and then subjected to hydrolysis, during which the acetyl group is hydrolyzed to form the alpha beta unsaturated carboxylic acid called protonic acid. And last time we saw that this type of a reaction involving an active ethylene compound as the nucleophile attacking on an active aldehyde or a ketone is given the name no-Enagel condensation or no-Enagel reaction, and has extreme synthetic utility in synthetic organic chemistry. Let us now consider the conversion of our ethyl acetoacetate molecule to a ketone. Now this should not be surprising because the ethyl acetoacetate molecule also has a ketonic group. So therefore it should be possible for us to convert to the desired ketone, and as an example we have chosen butanone. First step is as usual the removal of the acidic hydrogen by using a base. Once the carbanion is generated, it will attack the electrophilic carbon of the haloalkane, and you can already see that we have almost got the product that we want, which is CH3CO, CH2CH3. So this part will become butanone. So our job is now to remove this ester group. And to remove the ester group, unlike in the previous cases where we were removing the acetyl group, now we are more interested in removing the ester group. Therefore we will go for acid hydrolysis. Now under much milder conditions of acid hydrolysis, the acetyl group is not hydrolyzed, the ester group becomes COOH. So once it becomes, say, COO and H, then it will undergo decarboxylation. We have already seen this when seeing considering the reactions of diethyl malonate, that decarboxylation is easy because the carbon, which is negative now, can be stabilized by resonance by C double bond O. So our job therefore is to take the ester group, convert it to COOH, and then heat. Upon heating, decarboxylation takes place with the formation of butanone, carbon dioxide and ethanol. So we have considered a few simple examples of how ethyl acetoacetate can be acted upon to give us monocarboxylic acids, dicarboxylic acids, their derivatives, alpha beta unsaturated acids by no-Enagel reaction, and finally butanone or any ketone or substituted ketone by very simple steps. Thus, active ethylene compounds form a very important class of organic compounds which are very much useful in the synthetic scheme of things to make carbon-carbon bonds. They are highly versatile, useful, and therefore of great importance, particularly in the industrial organic chemistry. Thank you.